So, good day everyone. Today we will be discussing about shell sort. It is an improved version of insertion sort and it was created by Donald Shell in 1959. So, shell sort is a big idea to compare and sort elements that are far apart list. Imagine quickly sorting a messy pile of books by first separating all A's from Z's. Then it gradually reduces this gap between comparisons. So this diminishing gap approach lets element jump large distances towards their correct spot quickly. So when the gap finally becomes 1, like a regular insertion sort, the list is already nearly sorted, making the final step very fast. So it much faster than basic sort like bubble or insertion sort while still being straightforward to understand and implement. So what is shell sort? What exactly is shell sort? Shell sort is developed by Donald L. Shell in 1955 and it's one of the earliest sorting algorithms designed to fix the inefficiencies of basic insertion sort. So, Shell's key innovation was using a decreasing sequence of gaps. So, instead of comparing adjacent items, it starts by sorting elements that are far apart. So, this greatly reduced the number of shifts needed as items can move across long distances quickly. So, this makes shell sort significantly faster than simple algorithm like bubble sort and the standard insertion sort. So especially from medium-sized data sets, it's important to know that over the years, researchers have continued to develop various gap sequence to make it even more efficient.
Let's talk about the time complexity of shell sort. So shell sort performance depends on a gap sequence used or how far apart the elements are during each pass. So if we use the original method, we are simply cutting the gap in half each time. So the worst case time complexity is O of n squared. This means that for a large data sets, shell sort would still be slow. However, if we use Hibbard's and Sedgwick and Knuth propose the better gap sequence, these are more efficient and allows the algorithm to skip unnecessary sort comparisons. For example, you have a long row of a book on a shelf and they are all mixed up. Your goal is to arrange them in order by title. So instead of going one by one, like insertion, shell sorts takes a different approach. It starts by comparing the first book far apart. So for example, every fourth book, if any are out of order, it swaps them. So then the gaps sequence becomes smaller. Maybe every second book and it sorts again. So eventually, it does a final comparison neighboring books. So this method helps moves closer to their correct position early and especially if they are far from where they should be. It's like cleaning the mess, big steps first and then doing it in a fine tuning. So when we use the gap sequence or the improved gap sequence, shell sort can perform faster with a best case complexity of ON log n, especially when the lists are nearly sorted. So depending on how we choose the gaps and how it is arranged, shell sort can either be just okay or surprisingly fast. So this makes it a flexible and interesting sorting algorithm.
Hello everyone. At this moment, I will be explaining the real concept of shell sort using this simple simulation. I will be using random unsorted list. First, let's use a simple array named age, which have the elements of 44, 23, 42, 33, 18, 54, 34, and 16. So, the formula of getting its first gap is n divided by 2, which n represents the length of our array. So considering that our array has 8 elements, it will become 8 divided by 2, which will be picking every fourth element of this list. So the first pair will be 44 and 18, that will be our first group. Next would be 23 and 54, that will be our second group. 42 and 34, our third group. And lastly, 33 and 16 will be our fourth group. After pairing every fourth element in our list, we will perform insertion sort to partially sort every pair. So first, 44 and 18 will now become 18 and 44, 23 and 54 will remain 23 and 54. 42 and 34 will now become 34 and 42. And lastly, 33 and 16 will now become 16 and 33. After that, our array will look like this. Take note that it is not the final position of our list. We're just partially sorting to move the elements to their correct position. After that, let's continue to close the gap by using our formula, the division of 2 that will result into 2. So now, let's do every second element. So just based on the color we provided in this simulation. So our first group, let's consider this as first group, which are 18 and 34 and 42, 44 and 42. Our second group will be 23 and 16 and 54 and 33. Same as what we did the previous slide, we'll do insertion sort. So 18 and 34 will remain 18 and 34, and 44 and 42 will now be 42 and 44. Next is 23 and 16 will now 16 and 23, and 54 and 33 will now become 33 and 54. So our list or our array will now look like this. So as we can see, this array or list is considered as a almost sorted list. So let's finally do one more insertion sort with these all elements. So as what I've said, this will become very fast because it is almost sorted list. So we'll just do a insertion sort to finally sort this list, and our list will now become sorted after doing that. So that's how shell sort works in a randomly unsorted list. So the next cases will be furtherly discussed in the next slide. Thank you.
Hey everyone! Today we're going to look at how shell sort performs in two types of arrays. One that is reverse sorted and one that is nearly sorted. So first is reverse sorted list. So we start with the array age. So this is a reverse sorted list, meaning the elements are in the exact opposite order of what we want. So shell sort picks a gap, in this case 4. So we take every fourth element to form groups. So first group is 90 and 50. Second group is 80 and 40. Third group is 70 and 30. Fourth group 60 and 20. So each of these small groups is sorted individually. This greatly reduces the number of movements needed later when you reduce the gap and do a final insertion sort pass. So after that, our array becomes like this. So now we reduce the gap to 2. So that means we compare and sort every second element. So groups are formed like this. So first group 50, 30, 90, and 70. Second group is 40, 20, 80, and 60. So now the updated array becomes 30, 20, 40, 50, 70, 60, and 80, and 90. Again, by sorting these small steps, the array becomes closer to fully sorted because we reach the final step. So now we use a gap of 1, which is just a regular insertion sort since most of the work is already done. This step is quick and efficient. So finally do one more insertion sort with all elements. So insertion sort corrects the remaining inversions like 30 and 20. So our array will look like this. So now, early sorted list. So we start with the array age. So age is equals to 10, 20, 30, 50, 40, 60, 70, and 80. So this is an early sorted list. Most elements are in the correct order except for a small inversion, which is 50 and 40. So shell sort picks a gap, in this case 4. So we take every fourth element to form groups. So our first group is 10 and 40. Second group is 20 and 60. Third group is 30 and 70. And our fourth group is 50 and 80. So each of these small groups is checked, but no swaps are needed because they're already sorted. So no changes made. So this confirms the list is almost ready, even with just the first pass. So our array stays the same. So now we reduce the gap to 2. That means we compare and sort every second element. So groups formed, first group is 10, 30, 40, and 70. Second group is 20, 50, 60, and 80. And again, no swaps are needed. So no changes needed. So shell sort recognizes this and prepares for the final pass. So our array still remains. So final insertion sort, now we use a gap of 1, which is a regular insertion sort. So since the array is nearly sorted, only one small fix is needed. So this step compares every adjacent element. So just like insertion sort, ensure the array is finally sorted. So let's go through the steps. So let's compare 50 and 40, and after we compare them, we swap them. So it spots that 50 and 40 are out of order, so it swaps them. So the rest are already in the correct place. So no further swaps were needed for the remaining elements. So that is our final sorted output.
In conclusion, this simulation proves that shell sort is an efficient and adaptive algorithm. It varies the effort it exerts on how the data is being scrambled, working harder when it's necessary, and taking shortcuts when the data is almost sorted. While there are other algorithms better than shell sort when it comes to large datasets, it still perform well and did its job efficiently. And this is how shell sort shines. And I think this concludes our short presentation and simulation on what is shell sort and how it works. Good day and thank you.